Surprise, I lied at the end of the last video. We're actually not going to get into differential geometry quite yet, because I realized there's actually some stuff we can talk about with tensors in terms of just the linear algebra before we go on to manifolds to talk about the real definition of tensors as they appear in physics. So in this video, we're going to do just a little bit of bookkeeping. We're going to talk about the commutativity of tensor products, the associativity of tensor products, and what it means to be a multilinear map. It's going to be a little bit hand wavy. And then in the next video, we're going to specialize to vector spaces, and you'll even see the basics of the transformation law of tensors, except there's still a key component missing for the full-blown version in physics. The first thing we're going to touch on is the commutativity of tensor products. So the claim is that M tensor N is going to be isomorphic to N tensor M. So of course, in this video, I'm still talking about, the full general case of R modules. Again, if you're not comfortable with that, imagine that M and N are just real vector spaces. So in order to prove that these are isomorphic, well, one way to do it is to give an isomorphism. And recall, in the sense of categories, we normally, although for many examples we care about, it's just, some sort of map with that given property that is both injective and surjective. A more typical categorically minded way to phrase this is to give a pair of mutually inverse maps. So in the case of R modules, we want these both to be R linear homomorphisms, where they both compose to the identity, right? So if we applied phi then psi, that should just be the identity on A, and the other way around should give us the identity on B. So that's what we're looking for, to construct a pair of maps that satisfy this. Okay, well, here's a great example of actually using the definition of the universal property of tensor products. So let's take M cross N, and we define a map phi to go to N tensor R M, and this is going to be the map that simply, so we define it so that phi of M N is equal to N tensor M. And in order to use the universal property of tensor products, we need to prove that this is a bilinear map. So we have, I'm just going to show this in one component. The proof in the other component is entirely similar. So this would be something like phi of M1 plus alpha, some scalar, times M2 being N. Well, we know that that is equal to, right, by definition of this map, this is, almost wrote things on the wrong side there. But this is going to be N tensor M1 plus alpha M2. But then because of the relations that we know exist on tensor products, this is N tensor M1 plus alpha N tensor M2. And then sure enough, we see that those are the appropriate images of phi applied to M1 N, alpha phi of M2 N. So then that tells us that using the universal property of tensor products, that tells us that this map factors uniquely through to give us an R linear homomorphism phi tilde. Now, in order to get the reverse map, so I'm not going to go through that in any sort of detail, but you can sort of guess what this map psi is supposed to be going in the other direction, right? Instead we're going to put N cross M here, and we're going to end up getting a map N M into M tensor N, and then it would be super easy to check that, say, psi tilde applied to phi tilde applied to M tensor N, we simply just unpack these definitions, right? So forced on us by the commutativity of this diagram, we know that phi tilde of m tensor n would precisely be n tensor m, and by the the corresponding diagram down here for psi tilde, we would get m tensor n back. So this composition of maps is the identity, and you would see the same thing if you were to apply psi tilde first and then phi tilde. So just a nice application of the universal property of tensor products. And so we see that, yeah, in fact, these are isomorphic as R modules. Slightly more involved is the proof of associativity. So that means, much like in associativity of multiplication, we want to prove that M tensor over R n tensored over RL is isomorphic to M tensor over R and tensor over RL. Okay. And we're kind of going to take a similar approach here. So I'll write first, I'm going to start with looking at just M cross N, and I'm going to define a map. So for each little l in big L, I'm going to define a map phi sub L, which is going to take us into M tensor N tensor L. And this map is going to act by taking, so phi sub little l of Mn, and you can probably guess what I'm going to map this to. This is going to map to M tensor N tensor L. And so again, in order to make use of the universal property of tensor products, I want to show that this is an R bilinear map. So I'm just gonna do the calculation in one component, and you'll see that it's basically the exact same thing in the second component. So we're gonna have phi sub L here of M n1 plus alpha n2. Okay, well, by definition, that is M tensor n1 plus alpha n2 tensor L. Okay, but now simply from the tensor product relations that exist in the tensor product of n and L, we know that we can expand this as M tensor n1 tensor L plus alpha times n2 tensor L. And then now from the relation that exists between M tensor product, this tensor product, we can split this thing open. And so we see that this is going to be M tensor n1 tensor L plus alpha times M tensor n2 tensor L. And then finally, we can see that in fact, this is phi sub L of M n1 plus alpha phi sub L M n2. Okay, and so by the universal property of tensor products, that tells us that we get a unique map, making this diagram commute, which I will call phi sub L tilde. Okay. Now we still want to, right, we're trying to get a map from this full thing over to here and to construct an appropriate inverse. So now I'm going to define a map from N tensor R cross L, again, just using the universal property of tensor products. And here we have capital phi going into M tensor R, sorry, N over R tensored with N tensor L. And I'm going to define capital phi so that it acts by taking M tensor N little l, and I'm going to define this as phi sub L of Mn which is, of course, working out. It's M tensor N tensor L. Okay. And in this case, well, I'm not going to, I've already done 2 cases of, one component of the bilinearity for you. It shouldn't be too hard to convince yourself from here, if, perhaps somewhat tedious, that this capital phi is a bilinear map. And so, again, using the universal property, see how great the universal property is? I mean, we just keep, again and again, we just keep throwing the universal property at these things, and we get the theorems that we want out for free. In fact, one of the nice things is, if you tried to just define this map by hand on this, triple tensor product, the issue that you run into is well-definedness, because remember, the tensor product, it's defined as these quotients. And so you have to make sure that things are well defined on the quotients. And what's sort of nice, if you use the universal property, you're really starting off as just from some, Cartesian product, and there you don't need to worry about well-definedness. So in case you're looking at all this being like, what's the point? Why don't we just define it directly? Well, that's why, because we're basically taking care of the well-definedness issue. So in order to get the isomorphism we need a map going in the other direction, which composes to the identity. I'm not going to go through this step by step, but it's basically the same thing. So we'll have n starting from n cross L. We take this map phi sub L, which is phi sub little m. So we get one of these maps for each possible choice of M, which is going to map into M. Okay, I'm going to start being lazy and dropping the ring from my tensor products. And then, of course, so this will, from the universal property of tensor products, this is going to induce for us a map from N tensor L into here, which we call phi tilde sub M. And then again, just, repeating steps of this process, what's going to happen is now we'll define a new map from M cross N tensor L, which we'll call capital psi, in the exact same way. So psi of M N tensor L, of course, is just going to be psi tilde lowercase m evaluated at n cross n tensor L. And then finally, the universal property of tensor products gives us this map from M tensor N tensor L, which will be psi tilde. And then like before that we did with this map, uppercase phi tilde, if we basically go through the definitions, just following from the universal property, we'll see that on simple tensors, phi tilde will take M tensor N tensor L, and that's going to send that to M tensor N tensor L. And then to show that we have a pair of mutual inverses, I mean, compose this with uppercase phi tilde, and then where does that go? Well, of course, that just sends us right back here. And similarly, if you switch the order of composition of these maps, probably not a big surprise when you work this out. This will also give you the identity, and so these are a pair of mutually inverse maps, and thus we have the isomorphism showing us that tensor products are associative. Now, one thing that bears mentioning here, so I warned you in the last video that you can't always just prove things on simple tensors and call it a day. In this case, we can. right? Because if these are mutual inverses on the simple tensors, then extending by linearity, it's going to be, they're going to be mutual inverses on a general linear combination of simple tensors. So this is actually fine, but you should mention, oh, we extend by linearity. It's things that, like, when it comes to, say, proving induction, improving injectivity, for example, that's something that is not sufficient just on simple tensors. So just as a final note for something we're going to use in the next video. So now that we have the associativity of tensor products, one could imagine taking a repeated tensor product, and there's no worry about having to put these anywhere. So the repeated tensor product also satisfies a universal property. I'm just going to state it quickly. So imagine we have some number of R modules, M1 up to MR, and we take the Cartesian product. And now we're going to have what's called a multi-linear map. So what I mean by multilinear, I mean, you could probably guess, right? So a bilinear map said you fix, for any possible choice, you fix one of the coordinates, you leave the other one open. That is a bilinear map. For multilinear, we're going to say the map that sends M to phi of, so fix some k minus 1, call this k, fix some k minus 1 elements, right? So this will be phi of M1 up to phi of Mi minus 1. M will go in the ith slot. This will be Mi plus 1 ... up to Mk, right? So we've picked a fixed M1 up to Mi minus 1 and Mi plus 1 up to Mk. And we're saying the map that sends M to this quantity here, this should be linear. And this should hold for any choice of elements going in the fixed components and for any component that you choose to be the fixed one. So that's what it means for a map to be multilinear. Of course, bilinear is a simple case of this. And then we end up having a map together with now writing the repeated tensor product. Again, this is a well-defined thing because now we've shown that it's associative. We'll give you a unique R linear homomorphism commuting with this diagram. So in the next video, we're going to take a look at how these maps, we're going to specialize to the case of vector spaces, and then we're going to take a look at how these things transform under a change of basis, much in the same way that we understand how normal linear transformations change under a change of basis.